yesterday we have seen that your just yesterday we have seen just hold on, I have to share my screen, right, right. Is it visible? Is it visible to all of you? Hello?
Yes, sir.
Okay.
Yes, sir.
So this is internal inductance. It is independent of the radius of the conductor. So it will be half into 10 to the power minus 7 Henry per meter. Now inductance due to external flux linkages, right? Suppose this is the conductor whose radius is R, right? Externally you take 2 points, one is P, another is Q, and right. So P point is at a distance D1 from the center of the conductor, and D2 is another distance from the center of the conductor, and this P and Q are 2 points, right? So any magnetic lines of force outside this conductor will link all the current of the conductor, right? Because it is outside that, this is conductor of radius R. So outside that your what you call radius R, I mean outside of this conductor, right? And it will be your what you call that, it will whatever magnetic lines of forces will be there, it will link all the current. So and magnetic field intensity in any way at any point from the symmetry, it will remain same, right? So whenever we write that Hx is equal to then I upon 2 pi x ampere turns per meter square, you take from center R, from center of the conductor at a distance x, right? So this is your and this small thickness is dx. Same philosophy will apply. That's cross sectional area will be dx into 1 meter square, right? Same philosophy yesterday whatever we made. And bx is equal to mu 0 into I upon 2 pi x Weber per meter square, because air is the medium, right? So and the flux outside the conductors links the entire current, I mean all the current inside the conductor I, and hence the flux linkages d lambda x is numerically equal to d phi x. Therefore, d lambda x is equal to d phi x is equal to this flux density into the area dx into 1, right? Same philosophy. That is mu 0 I upon 2 pi x Weber per meter length of the conductor. Now, if you integrate from your point P to point Q, that is D1 to D2, D1 to D2. So lambda PQ will be mu 0 I upon 2 pi ln D2 upon D1 Weber turns per meter. Right. Therefore, L external, that inductance, that will be lambda PQ upon I. That will be mu 0 by 2 pi ln D2 upon D1 Henry per meter. Right. So if you put mu 0 value, so 4 pi into 10 to the power minus 7 Henry per meter square, meter, right? Then L external will be 2 into 10 to the power 7 ln d2 by d1 Henry per meter, right? So this is external to the conductor. This is internal to the conductor, and this is external to the conductor, right? But in this case, it depends on the distance d1 and d2. For example, if d2 is equal to d and d1 is equal to r, say from the surface of the conductor, then this will become actually 2 into 10 to the power minus 7 ln d upon r Henry per meter, right? Just hold on, somebody wants to join, I think. Yes, Ajim Sohel. Yes. So now inductance of a single phase 2-wire line. First we'll consider single phase 2-wire line. One is incoming, another is outgoing. That means, for example, just hold on, just hold on. Piyush Kumar. Uh, So suppose you have two conductors, single phase, say, then and plus means that current entering into the page, right? That is, one is incoming, another is outgoing, right? And this plus means it is entering into the page, and dot means it is leaving the page. So this is incoming and this is outgoing, right? Assume that this current I1 and this current is I2, although I1 is equal to minus I2 according to the direction, and assuming that this radius of this conductor is R1 and radius of this conductor is R2, right? So this is actually the conductor can equal currents but in opposite direction. So basically I1 is equal to, it will be minus I2 because it is a return path, right? So if one is I1, another will be, then I2 is equal to minus I1, right? Now this current setup magnetic field line that links between the conductor as shown in this, right? So what we'll do, inductance of conductor 1, that means this is my conductor 1, due to internal flux is given by equation 2.1, that is half into 10 to the power minus 7 Henry per meter square, that is meter, that is there, right? But as a simplifying assumption, we can assume that all the external flux set up by current in conductor 1, I mean this one, links all the current up to the center of the conductor 2. I mean whatever is there, we will consider only up to the center of the conductor, right? Not beyond that, because if we consider, it is a fair assumption, right? If you consider beyond that, things you will not get much improvement in the result, but things will become your, what you call, derivation will become different then, right? So, and therefore we will consider up to center of this conductor. Similarly, if you think about this one, we will consider up to the center of this one, right? And this gives more or less quite accurate result, right? And these are the, and another thing is that d, this center to center distance is d, right? So d minus r1 approximately is equal to d. Similarly, d minus r2, if you think, it will be approximately is equal to d, because d is much larger than r2, r, radius of the conductor, right? Therefore, for this one, if we assume d1 is equal to r and d2 is equal to d, I mean this equation, d1 is r and d2 is equal to d, then L1, your L1 will be 2 into 10 to the power 7 ln d upon r1 Henry per meter. Therefore, the total inductance of the conductor 1 is then given by L internal inductance plus L1 external inductance, right? So, internal is really half into 10 to the power minus 7, and external will be 2 into 10 to the power 7 ln d upon r1. If you simplify this, so you take 2 into 10 to the power minus 7 common, then in bracket it will be 1 upon 4 plus ln upon d, ln d upon r1, right? So this term you can write ln e to the power 1 upon 4 plus ln d upon r1. Similarly, that means you can write 2 into 10 to the power minus 7 ln d upon r1 e to the power minus 1 upon 4 Henry per meter. That means if for natural log, you convert it to, that is from log base c, you convert it to log base 10. So from natural log, we are converting into log base 10. Throughout this, we will use actually log base 10, or we converted. If you convert this, you can easily do it. You can do it. So 0.4605 log d upon r1 dash millihenry per kilometer. Therefore, r1 dash is equal to r1 into e to the power minus 1 upon 4. That is 0.7788 r1, right? So therefore, the radius r1 dash is the radius of a fictitious conductor, which has no internal inductance but has the same total inductance as the actual conductor. Therefore, when you will solve the numerical for calculation of inductance, that if radius is given r, so you will take this r dash 0.7788 r, as if this is a fictitious radius of the conductor, as if it has no internal inductance, but whatever inductance gives, it includes the your internal inductance. So that's why r dash is equal to 7 points. In general, r dash is equal to 0.7788 r, right? Similarly, for L2 also it will be same thing. 0.4605 log d upon r2 dash millihenry per kilometer. Therefore, total inductance of the circuit, that means this one, incoming path and outgoing path, total, right? Total for the both conductors, it will be L1 plus L2. Therefore, if you do so, if you add this L1 and L2, you will find it will become 0.921 log d upon root over r1 dash into r2 dash millihenry per kilometer. If you assume both the conductors radius is same, that is r1 dash fictitious radius, that is r1 dash r2 dash is equal to r dash is equal to 0.7788 r, then it will be L is equal to 0.921 log d upon r dash millihenry per kilometer, right? So this is actually inductance of single phase circuit, right? One is incoming path, another is outgoing, right? This is a your exam will be open book, so you have to practice, because the way things may be given, that you need a lot of practice, right? Although formula, everything will be there in front of you, but you have to practice. Now this term whatever equation gives the inductance of 2R line in which one conductor acts as a return conductor for the other. This is known as the loop inductance because one incoming path, another outgoing. So it is giving a loop inductance. So this one we can write like this one, that L1, I mean this L1, your L1 is equal to whatever we got 0.4605 log D upon R1 dash, right? Or if radius is same, R1 dash is equal to R dash. So this one we can write L1 is equal to your 0.4605 log 1 upon R dash. We are assuming R1 is equal to R2 is equal to R. Hence R1 dash is equal to R2 dash is equal to R dash. Right. So this you can write log 1 upon R dash plus 0.4605 log D upon R. That means this is the inductance calculation from the radius R to 1 meter length from the center of the conductor. And this one from 1 meter to at a distance D. This way these two terms have been broken, right? So this way this term, this L1 is written. Similarly, for L2 also 0.4605 log 1 upon R dash plus 0.4605 log D upon R millihenry per kilometer. Now, as both the conductors are identical, therefore L1 is equal to L2 is equal to L. Therefore, inductance per phase per kilometer length of line is given by that L is equal to 0.4605 log 1 upon R dash plus 0.4605 log D upon R millihenry per kilometer. Right. So, from equation it is clear that first term is only the fraction of the fictitious radius of the conductor. First term of equation can be defined as the inductance due to both the internal flux and that external to conductor 1 to radius 1 meter. It is 1 to R dash means this one is 1 meter, right? The second term in this case is dependent only upon the conductor spacing and this is known as the inductance spacing factor. This way these two have been, instead of single term, we have written these two terms, right? Now, why we have done so, little bit just for the sake of little bit of clarification, the self and mutual inductance. Suppose this is a coil, this is a coil. Suppose these two dots you have made, current is entering into the dot, this I2 is entering into the dot, but if it is current is I1 is going, then the I2 will be coming out, so I1 will be minus I2. And this is self inductance L11 and this is L22 and mutual inductance is M12 is equal to M21. Right. Therefore, flux linkage of lambda 1 and lambda 2 can be written as lambda 1 will be L11 I1, right, because of its current is I1 plus that mutual inductance is M12 due to the current I2, so plus M12 I2. Similarly, lambda 2 you can write lambda 2 is equal to second term is L22 I2 plus M21 I1, right. Now, this current is going in and this is actually out. I1 will be equal to minus I2. So if it is so, I2 is equal to minus 1 if you substitute, then L1 lambda 1 will get L11 minus M12 I1 and lambda 2 will get minus M21 plus L22 I2, right. So one is self, another is mutual. Then if you now, therefore we can write L1 will be equal to L11 minus M12 and L2 will be L22 minus M21. Right. Now compare equation 40 and 41 with 33 and 34. Then you will get L11 is equal to L22 is equal to 0.4605 log 1 upon R dash millihenry per kilometer and M12 is equal to M21 you will get 0.4605 log 1 upon D. Right. Because here it is D upon your what you call D upon 1, right? It is D upon 1, but minus sign is there. Here minus sign is there, minus sign is there. That's why it is your what you call, that is your 1 upon D, right? So this is actually mutual inductance and this is actually self inductance, right? The above described approach of self and mutual inductance can be extended to a group of conductors, right? So this is actually this kind of expression. When I was writing the book, in common textbook, you will not find, which is, I mean, wherever books are there, you may not find this kind of thing. But after searching several books, when I reading the book, I think references, I have cited those references at the end of this book. I think from somewhere, I saw this explanation is much better than any other textbook available, right? So, because this helps actually, if you know only one formula, you can write everything. Just you will see that. Today I will take class up to 10:35, right? Today I will take, I have some work and Monday I will not take class. Wednesday I'll take as it is, right? Next Monday also I'll not take due to some reason, and next Wednesday will be as usual. Anyway, come to this. Today also maybe up to 10:35, not more than that. The above described approach of self and mutual inductance can be extended to a group of conductors. Suppose in a group of conductors you have n number of conductors. Therefore, you can write I1 plus I2 plus In is equal to up to In is equal to 0. Right. So generalized formula for flux linkage of conductor I is given by whatever you have seen here, lambda 1 L11 minus M1 to I1, lambda 2 minus M21 plus your L2 to I2. In general, here lambda 1 L1 and M1 lambda 2 is equal to this one. In general, when we write, it will be lambda I, right? That is of conductor I is given by LII plus sigma j is equal to 1 to n, j not is equal to I, Mij, your Ij, right? So this way you can easily write that this thing, it should be always in your mind. Later when I take some your hot three-phase circuit on this that, those equations will be written from this one and this one only, nothing else. So for flux generalized formula for the flux linkage of conductor, it can be given as lambda, that is two conductors we choose, but in general it will be LII plus sigma j is equal to 1 to n Mij Ij, j not is equal to I, or whatever equations we have seen for flux linkages, right? Whatever you have seen here, inductance L1, L2, everything, right? Right, L1 we have got this one, right? L1 we have got this one. This is for just considering your what you call one conductor. This is another conductor, right? But when you will take that generalized thing, that flux linkages, because there you are considering, if you consider here only two conductors, you can do it and see the formula. So that flux linkages of conductor I, you can write 0.4605 II log 1 upon Ri dash plus sigma j is equal to 1 to n, j not is equal to I, Ij log 1 upon Dij milliweber turns per kilometer. This way it has been written, right? So whatever you have seen here, that in this what you call in this expression, this is actually L1 L2, right? But lambda is equal to Li, you know, right? So basically here only two terms, but when lambda I for ith conductor will come, so flux linkages will be your lambda I is equal to 0.4605 in bracket II log 1 upon Ri dash plus sigma j is equal to 1 to n, j, but j not is equal to I, Ij log 1 upon Dij milliweber turns per kilometer, right? This formula and this formula we need again and again, right? Then actually after reading several books, I got it from somewhere. I told you in common textbook this formula will not be there, but if you know this easily, I mean this is very clear, and if you know this easily, you can write for any number of conductors 3, 4, 5. Similarly, when we'll do the capacitance, I'll give you another formula. There also directly you can make it, right? So this is actually flux. These two equations, or two equation 2.45 and 2.46, we will be needing again and again, right? So particularly this one 2.46, right? Because we when you consider three-phase transmission line or group of conductors, at that time this will be very useful. The 2.545 or 2.46. Again and again, I will not go back to this equation, but I'll quote that from equation this we are writing, right? Now, another thing is the type of conductors. That conductors, you can get many good conductors, but you have to see the cost benefit analysis. Generally, for high tension transmission line, basically they use ACSR conductor. ACSR means aluminum conductor, steel reinforced. That means central conductor is a steel such that tensile strength will be very high, and around it the spiraling will be aluminum conductor, right? So it is aluminum conductor, steel reinforced. That is your ACSR conductors, right? These, although many others are there, hollow copper conductors, standard conductors, but you have to see the cost benefit analysis. At the same time, you have to see the weight should be less, right? Because tower to tower, sometimes towers are 200 meters, 300 meters long, and each conductor is connected to that. If the weight of the conductor is high, then sag will be much higher, right? it will come down. It will be like to some extent parabolic shape, right? But if tensile strength is less, in that case, what will happen? The distance between the tower will reduce, cost will increase. But if you use aluminum conductor, steel reinforced ACSR conductor, then distance between the towers, depending of course on the voltage level of the your what you call. Just hold on, if anybody is joining or not, or it is my mistake. Just hold on. No, nobody. Right. So it depends on the your what you call. If tensile strength is good, then distance between the two towers will be more, such that your number of towers erected it will be less. So cost, your cost benefit analysis, if you think, so investment cost will be less. So generally they use ACSR conductor because it is cheaper than the copper conductors of equal resistance. Corona losses will not teach. Whatever COVID corona you are reading, right, that is different. And this corona loss is due to the ionization of the conductor, right? When it carries, when it your what carries current, and dust formation will be there, or this thing, that thing, and air will be ionized around the conductor, and corona loss will happen, right? But that is not whatever COVID corona, but this is a standing your standard thing more than 100 years, right? And later at the end, I'll tell you that how one can visualize corona. I mean, you can see it in the rainy season, another thing, some chattering noise and some violet glow around the conductor. And you can see that due to that, that power loss will be there. So coronal losses are reduced because of the larger diameter of the conductor. There is no formula for that, but some empirical formula is there. And based on some testing result, they have come to this conclusion. And it has superior mechanical strength and hence span of larger lengths, which result in smaller number of supports for a particular length of transmission line. So how actually it will be done? The radius will be such that this is a central conductor, right? So here actually so many layers are there. The first layer is steel, second layer is also steel. First one is 1, second will be 6, 7, next one will be 12. Automatically will come, it will be 19, and overall then another one will be 17, so it will be 36 and so on, right? So to increase the tensile strength, if so many layers are there, this will be steel, right? Steel strands, and these are aluminum strands. And there is a formula: the total number of strands is in S in concentrically stranded conductor with total annular space fitted with strands of uniform diameter d. That is S is equal to 3y square minus 3y plus 1. If y is 0, S is equal to 1. That means the first one. If y is equal to 2, then 12 minus 6 plus 1. So 1 plus 6, so 7. Around this, 6 are there, 7. If it is 3, then 27 minus your 9, your 18 plus 1, 19. So this one plus this one plus this one will be 19, next one will be 36 and so on, right? And diameter will be, in general, overall diameter will be, remember, whatever will be the sketch or diagram you see that looks like that this diameter is different, but let me tell you, or diameters, all the diameters will remain same. Or this diameter, the aluminum or steel, their diameters are same, but a diagram, the draftsman who has drawn this, perhaps he doesn't know when it was given to the press, but diameters of all these conductors are same, or radius. So overall diameter you can easily calculate. It will be 2y minus 1 into d. D is the diameter of the single conductor. So diameter of this conductor, all these conductors will remain same, right? And this is how this formula is: S is equal to 3y square minus 3y plus 1. Y is the layer, right? So this is actually, if you have voltage level is very high, the number of strands will be more, right? Aluminum strands will be more. It depends on the design. And inductance of composite conductor. After making this, today I have to take leave from you, and I will after explaining this, and then I will start again from next Wednesday. Monday I have some work, right? So now you assume a group of conductor. Suppose this is composite conductor group. There are n number of conductors are there, A, B, C, D, up to n number of conductors are there. This is another composite conductor group Y. Here A dash, B dash, C dash, up to m number of conductors are there. Right. So we have to find out that what is the flux linkage of each conductor. Now we'll go back to that equation. I mean this equation that is your 245 or 246. We'll go back to 246. Right. Using this formula, directly you can write. First thing is, look, what you assume, actually, just 1 minute. Actually, these conductors all are in parallel. All are in parallel means Actually, just hold on. Uh, for example, this is coming. This is conductor A dash. This is B dash A B C, and this is your A B C N dash, right? This is a group X, right? That means they are in parallel. Similarly for other one also. Similarly for other one also, it will be your A dash. It will be your B dash. It will be your C dash up to M. This is N and this is M, right? They are in parallel. So if this current entering into this one is I, if current is entering I, and you have such N number of conductors, then each one will carry current I by N, right? Similarly here, if total conductors is M, is current minus I, it will be minus by I by M, because one is incoming, another will be outgoing. So if I taken direction this way, in this case it will be direction this way, right? So that's why whenever whenever we have taken, that's why it is taken I by N. Total current is I, but each conductor is carrying I by N current, and using that formula A, B, N, D, N, the log 1 upon Rx is taken. Rx is the radius of the conductor A, right? And assume that it is Rx dash because fictitious radius plus log 1 upon DAB, it is equation 246, right? Plus log 1 upon DAC up to log 1 upon DN. And apart from that, this is also there. This current will be your I by M, but direction here current will be minus, right? Because it is opposite direction, so it will be minus 0.4605 I upon M log of 1 upon dA dash, right? That means from here to here dA dash, then dA dash your what you call so dA dash, then DAB dash, right? So DAB or what you call B dash, then D your C dash, and so on, right? So 1 upon dA dash plus log 1 upon DAB dash up to log 1 upon DAM, right? So this way it will continue. Now if you simplify, then flux linkage of conductor A, I mean group A, it will be 0.4605 I log. Here it all the product will come to the power 1 upon M. You can simply do it, right? Because it's minus, it will go to the numerator. And here Rx dash, all the product to the power 1 upon N, it will be in the denominator, right? So inductance of subconductor A will be then lambda A divided by I by N, right? Because here it is lambda A, but each conductor is carrying, I told you, each conductor is carrying that your I by N current, right? So whenever you do, then lambda A should be, because N is there, 0.465 N, because total current is I, right? But for each one, that is current is I by N. So it should be divided by I by N. II will be cancelled. N will be product here. So that's why it is your 0.4605 N log of this one, right? That is LA. Now, the average inductance of any one subconductor of composite conductor X is that you calculate all divide by N. Right, L average will be LA. This is LA we have calculated. Similarly, LB, LC, LN, all you can compute. But after that, you take the average inductance because they are in parallel, so you divide by N. Right. So LA plus LB plus LC up divided by N. Since conductor X is composed of n subconductors, right, electrically in parallel, its inductance is Lx will be L average upon N. So basically, it will be, because if each conductors you are having your L average, right, then you have n number of conductors, so it will be L average by N. So it will be basically LA plus LB plus LC up to Ln upon N square, right? So substitute all LA, LB, LC. I mean, here it is shown LA only. You have to calculate LB, LC up to LM. Here it is not shown, right? You little bit try, right? If you do so, then LX will be, you will be is equal to your 0.4605 log dm upon dsx m millihenry per kilometer, right? Therefore, dm is the this product of this to the mnth root, and ds6 is the n squared root, right? And all dA, dBB nothing but the fictitious radius of the conductor of the group X. This is little bit you try. Later I'll take some example, right? Sorry. Therefore, dm is the mnth root, and it is called your mutual GMD, because the distance between your what you call it is between two groups. This A dash, AB dash, these are a distance between two groups. So this is called mutual geometric mean distance, right? And here dsx actually distance of the conductor in each of their own group. DB all are fictitious radius, AB up to AN. This is called self, that is your call your self geometric mean distance. That is self GMD. And this is called mutual geometric mean distance. Mutual means distance between the two groups conductor. And self means that the distance between the conductor in one particular group. Right. So dm upon dsx your millihenry per kilometer, right? And this way one can calculate. So question is that little bit practice is necessary, and my NPTEL course online it is there, right? And there several examples are taken, and several color pen, red, yellow, blue, all I have used. If you have a time, because I know you have many courses, I understand that, right? If you have a time, you can also see this. So today up to this, again we'll meet on your what you call Wednesday, right? Because Monday I'll be busy, right? And Wednesday we'll start again. Thank you very much for today, right? So thank you then.